welcome to this POTSI satellite workshop on distributed algorithms on realistic networks, network models. Our goal was to bring together researchers working on different aspects of real networks. So we hope that the workshop can initiate some new cross-field collaborations, especially across the fields of distributed computing, structural graph theory, especially the newly emerging sparsity theory, network science. And in particular, we hope to see some practical implementations, evaluation, and the use of structural graph theory in practice, and to initiate these collaborations between the researchers. So today we have 3 tutorials of 90 minutes for you. These tutorials shall provide accessible introductions to the various topics, and then we furthermore have 5 contributed talks of 30 minutes. You can find the schedule on the webpage. Our first speaker will be Thomas Bla, who will speak on the theoretical algorithm analysis meets practical data. So let me introduce Thomas. Thomas Bla studied computer science at the Karlsruhe Institute of Technology, KIT, where he continued to do his PhD in the field of graph drawing. And then he spent 5 years as a postdoc at the Hasso-Plattner Institute in Potsdam, HPI. And since then, his research focuses on the analysis of algorithms on realistic input models, with the aim to bridge the theory-practice gap between theoretical lower bounds and efficient practical algorithms. Now, quite recently, Thomas became a junior professor in Karlsruhe at the KIT and is now the head of the Scalable Algorithms Group at the KIT in Karlsruhe. So, please, Thomas, the stage is yours. I'm very excited to see what you are going to present to us.
Yeah, thanks for the nice introduction. I'm mainly going to talk about the theoretical analysis of algorithms. And I want to start out by discussing 3 questions. First, why do I think a theoretical analysis of an algorithm is useful even for practical purposes? Second, does it always work, or are there cases where the theoretical analysis kind of fails? And third, in these cases where the theoretical analysis fails, can we somehow fix it, and how can we fix it? Okay, so let me start by the question, why should we do a theoretical analysis? And I want to start with a very simple example, sorting numbers. So assume we have n numbers and we want to sort them, so this should be the output. Then there are, of course, different algorithms to choose from. One being bubble sort, and we all know bubble sort has quadratic running time, so our theoretical analysis tells us the running time is n to the power of 2. On the other hand, I can, for example, look at merge sort, and there again, I can do a theoretical analysis, which tells me, okay, the running time will be n log n. So what does this tell me? Well, it tells me that if I look at the speed up of merge sort over bubble sort, then the speed up will be something like n over log n. So merge sort will be a factor of almost n faster than bubble sort if I look at large instances. So why is this useful for practical purposes? Well, now if I have to choose a sorting algorithm and I know I have a bunch of numbers to sort, then I certainly should use merge sort, and I can basically ignore the existence of bubble sort. So I can focus my development of algorithms on the part that is good for me, meaning on the algorithms that are fast. Different example, vertex cover. The problem vertex cover is to, given a graph, and we should delete as few vertices as possible such that no edges remain. And one way to do that, which is not always optimal, but certainly a reasonable heuristic, is to do a greedy algorithm that deletes the highest degree vertex at every point in time. Because we want to delete all edges in the end and we want to remove as few vertices as possible, it's a good idea to remove as many edges as possible with each step. So removing a vertex with a very high degree is a good idea. In this case here, this vertex has degree 5 and all other vertices have a lower degree. So in the first step, I would just delete this vertex. And now deleting this vertex decreased the degree of these vertices, for example. So this vertex no longer has degree 4, but only 3, and this vertex has degree 4. So in the next step, I would delete this vertex up here. And I continue, the next one is this one with degree 3, and so on. And in the end, I don't have any edges left, and I have a solution to my vertex problem. Now, if I want to implement that, then I again have different ways to do that, right? I have plenty algorithms to choose from, basically, or I have to develop my own algorithm. And if I do it in the naive approach, then I would, in every step, look for what is the vertex with the highest degree, and then I remove this vertex. Looking for what is the vertex with the highest degree takes, say, linear time. I look at every vertex, look at what's the degree of the vertex, and then I have to delete the vertex, and I do that a linear number of times. So I have n times n steps, so I have theta of n squared running time. Now, if I'm a bit more clever, then I use a priority queue to keep track of the degrees of the vertices. And in the priority queue, I can very quickly ask the question, what is the vertex with the maximum degree? And then I can just delete this vertex. And if I do that, I get a running time of n log n plus m, and m is the number of edges here. So n is the number of vertices, m is the number of edges. Again, I can ask, okay, what is the speed up? And I see in this case, it's a bit more complicated because I have these two terms here, and the running time of this implementation depends on which of the terms is dominant. But the speed up I get is either n over log n, so again, similar speed up to merge sort over bubble sort, or my speed up is n squared over m, so number of vertices squared over the number of edges. Now, if I have a very, very dense graph, then m is n squared, which means that I don't have an asymptotic speed up, meaning my speed up doesn't increase for increasing graph size. But unless I have this special case, my speed up is asymptotic. So meaning if I choose a larger instance, I get a larger speed up. So say you want to do experiments and prove experimentally that this implementation is much better than this implementation, and you want to aim for a certain speed up. Say you want to say this implementation is 5 orders of magnitude faster than this implementation, then you can certainly do that. You just have to choose your instances sufficiently large, because the larger you choose your instances, the higher your speed up is. Why is something like knowing this useful? Well, I mentioned already, if I know that a certain algorithm is much better than another algorithm, I can ignore the worst algorithm and focus on the better algorithms. So predictions for the running time help me to avoid a lot of comparisons, a lot of experimental comparisons, because I mean, I don't need to experimentally compare bubble sort and merge sort to know that merge sort is better. So I can save a lot of time by looking at or thinking about what will the running time be of my algorithm. And if I notice I have one algorithm that's asymptotically better than another algorithm, then the asymptotically better algorithm is probably the one I should choose. Okay, so the practical use, or the main direct practical use, in my opinion, for doing at least some amount of theoretical analysis on algorithms is to have predictions for how good different algorithms are, and you can then use the predictions to guide your practical experiments. Okay, does it always work? This was my second question. And to discuss the second question, I have another example, again, a very basic algorithm. I want to find the shortest path in a graph. So let's say I have an undirected graph and it's unweighted. So to compute the shortest path, I can just do a breadth first search. So I have my vertex S and my vertex T, and I want to have the shortest path from S to T, and the breadth first search first looks at all the neighbors of S, then at all the vertices of distance 2 from S, vertices at distance 3, and so on, until I see the vertex T, and then I can backtrack from T and find the shortest path from S to T. And this takes linear running time. So I have to look at the whole graph once, basically, but not more. Now there's one heuristic you can use to try to speed this up, which is the bidirectional search. So instead of searching only from S until you reach T, you search from S and from T simultaneously until the two search spaces meet. So you look at the neighbors of S, at the neighbors of T, at the vertex at distance 2 from S, at the vertex at distance 2 from T, and so on until the search spaces meet. And then from the meeting point, you can derive the shortest path. You can backtrack and find the shortest path between S and T. Now, again, if you do the theoretical analysis, you have to look at the whole graph, so you again get a linear running time. Now, the speedup is theta of 1, so constant, so it's not so clear which algorithm is the better algorithm. So it seems like the theoretical analysis doesn't tell you a lot here, but I would argue it still tells you something. It tells you that the speedup is independent of the graph size. So if you have growing inputs, then the speedup doesn't improve. So if you have say you have the bidirectional search as a subroutine, and you have instances that are so large that they are so far out of reach for you to solve them, then this tells you that the bidirectional search probably won't help you, because it only gives you a constant factor, and this is probably not enough to reach these instances that are far out of reach. So if you have instances that are so far out of reach that you need to improve in the asymptotic, then the bidirectional search won't help. Let's compare this to what you observe in real-world networks. So I have some experimental results on real-world networks here for you. And what I did is I just took some real-world networks of varying size. So I start with networks with 32K edges and go up to 50-100K edges. And the number of edges is also color-coded. So the greener, the smaller the graph, and if you go towards the red side, then the graph gets bigger. And on the x-axis, you have the speed up of the bidirectional search compared to the unidirectional search. And what you can see is that the speed up seems to be between 1 and 3. So if you say, okay, I'm up for saving a factor of 3, then this basically tells you, okay, then go ahead and implement the bidirectional search. But again, you shouldn't expect to solve instances that are far out of reach by using the bidirectional search instead of the unidirectional search. And this coincides with what the prediction tells you. So the prediction matches what we get in practice. Now, what I have to admit is that I kind of cherry-picked these instances. So I didn't pick these instances one by one so that they work this way, but I kind of picked instances that have certain properties where I knew kind of that they would probably behave like this. And I hope in the end of the talk you know how I did that and would also be able to do that. If I cherry pick the instances somewhat differently, I get a very different picture. So again, I have a bunch of networks with increasing graph size from the top to the bottom, and you can already see that the speedup is much higher. It goes up to almost 400. And I think the more important part is that the speedup seems to increase for increasing graph size. Of course, you have a little bit of noise, but because different networks have different structure and behave differently, but you get this increasing speed up for increasing graph size. And this clearly doesn't match the prediction that we have a constant speed up. So with this in mind, it might be that using the bidirectional search can help you to solve problems that were out of reach before. So the observation is that the prediction of the theoretical analysis is quite wrong for some type of instances. And in this case, you could say, well, I mean, this is not really a problem. It's a nice surprise, I would say, because the bidirectional search is much faster than I expected it to be. And by being so much faster, I can now solve problems that were probably out of reach before. And this actually has been done. So you can compute between centrality, for example, for rather large networks rather quickly and quicker than you should be able to with respect to the theoretical analysis. Now, given that this is a nice surprise, I still don't like surprises. So I want first of all, I want my theoretical analysis to be kind of accurate and predict the what I see and practice correctly. But this is maybe just my point of view. But I think it actually harms the practical use of my theoretical analysis, because if I look at the slide before where I did the analysis and said, okay, I have a constant speed up, so probably it's not really worth it, at least not to, or at least I shouldn't hope to solve instances that are out of reach by using the bidirectional search. So maybe it's not worth to implement it, and then I don't implement it and I miss out on the huge speed up I could have gotten by implementing the bidirectional search. So maybe the theory guides me in the wrong direction and tells me, well, you don't need to look at the bidirectional search, while in fact I should have looked at the bidirectional search. And once we are in this situation, it's kind of a bad feeling, right? Because now the question is, how helpful is the prediction anyways? Do I now need to start implementing bubble sort to see if it's really slower than merge sort? Well, I mean, certainly not, because this theoretical analysis often works very well. So I don't want to say that it's always bad, and it often helps you a lot to steer you in the right direction. But in some cases it doesn't. So oftentimes you still should try different things to figure out how it works in practice, and the theory doesn't give you as good of a guidance as we would like it to give you. Okay, so the predictions are wrong. The question is, why are the predictions wrong? Well, the prediction is based on a worst case analysis, at least in the example I showed you earlier. There are instances where we need to look at the whole graph. So we have a running time that's linear in the graph size. But the real world might be nicer to us, so the practical data might be nicer than the worst case. And if this is the case, then the prediction can be off. Okay, I hope this answered at least the first two questions. I hope I could convince you that theoretical analysis can be very useful, even for practical purposes, and that it doesn't always work, but that it would be useful if we could fix it. So the question is, how can we fix it? And to answer the question, how can we fix it, I think we should first ask the question, what is an acceptable fix? And there are different techniques out there. I won't cover a lot of them. I focus mainly on one, but I first want to motivate why I focus on this one technique I want to discuss today. So to answer the question what an acceptable fix is, maybe we start with the best we can hope for and just wish some things and see whether we can reach that. So I would say the holy grail basically would be that we prove that there is some kind of property, and if the instances have this property, then the instances are easy. And additionally, I show that the practical instances I'm actually interested in have this property, so I've proven that the practical instances I'm interested in are easy. So in a picture, that basically means that I have my space of instances here, and I draw a line through the space of instances, and I say I prove that all the instances that are below this line, all the instances in the green region, are easy to solve, in the sense that there is an algorithm that or that the algorithm has a good running time on these kind of instances. And on the other instances, I maybe prove that the algorithm is not fast, so I have a divide between hard and easy instances. And what I then want to do is I want to place the practical instances in this easy regime, so that I basically proved that the instances I care for are easy. Maybe it's not always such a binary thing. Maybe we don't want to have just easy and hard, but we want to have some things in between, some shades of gray basically. Well, then we might have something like a parameterized approach, where the strength of this property is given by some kind of parameter, and depending on how large this parameter is, I have easy instances at the bottom, hard instances at the top, and in between I have in between instances. So this would be the ideal case, but I think I have to add another requirement to this list. And this additional requirement is that the property I want to look at should be natural. Natural is a bit fuzzy here, but what I mainly mean with that is that the property shouldn't depend too much on the algorithm I'm currently trying to analyze. So if I choose this property, for example, to be the running time of the algorithm I'm currently trying to analyze, then the result I prove is not really any result, because it just tells me, well, your algorithm is fast if your algorithm is fast. And this is not really good. So I want a property that's kind of natural and doesn't depend on the algorithm I'm analyzing. So I called this the Holy Grail, not only because it's the thing we want to have, but also because it's kind of hard to find. There are examples where you can achieve this, but oftentimes I think it's very hard to do. And the reason why it's hard is that you have two goals that are kind of contradicting each other. So the question is, how do I choose this property that separates the hard from the easy instances? I want to prove that all instances that have this property are actually easy. So among the instances with this property, I have to consider the worst case. So within this green regime, there cannot be any hard instance, because otherwise I cannot show that this regime is completely green. So the property I choose has to be sufficiently restrictive to exclude all the hard instances. On the other hand, if I make this property too restrictive, I maybe don't include the instances I'm actually interested in. So there are these practical instances, I want to place them in the green region, but if I make the green region too small because I have to restrict it so much, then maybe the instances I'm interested in are no longer in this green region. So I have this contradiction between I want to make this property very restrictive so I can prove something, but I don't want to make this property too restrictive because I want interesting instances to have this property. A weaker fix that I personally find very acceptable, I want to propose for the rest of the talk, is the following. Instead of drawing this hard line in the space of all the instances, we look at prototypical instances and we prove how the hardness of the instances or how the difficulty of instances depends on the property I'm interested in for these prototypical instances. So in this picture, this would mean that I maybe take out a slice of the space of all my instances, and I prove that if I have a certain property, then the instance is easy. If I don't have the property, I'm living up here, then the instance is hard. And I do that for a slice of somehow prototypical instances. And then my hope is that if I place my real world instances somewhere close to the instances that are easy with respect to the property, then I hope that my results on the prototypical instances generalize to the real world instances. So I don't actually prove that my practical instances that lives here has a good running time, that it's an easy instance. I can't prove that because it's not part of the prototypical instances. But at least I'm not surprised that it works well if it lives down here close to the prototypical instances. So I basically weaken my goal. I don't no longer want to prove that the instance that my practical instances, I don't want to give a guarantee that the practical instances are easy, but at least I don't want to be surprised if the practical instances are easy. And I think I can achieve this by doing such an approach. Now let's try to make this a bit more specific. So far this is kind of high level. So let me go a bit deeper and make this more specific. And in the end, I will go to and show you how this works, for example, for the bidirectional search. So the question was, how can we fix this? And the method I want to propose is that we assume instances. These are the prototypical instances I mentioned on the slide before. I want to assume that the instances are randomly generated. And then on these randomly generated instances, I do an analysis of the expected running time. So I don't say, okay, what is the worst case instance? What is the running time on the worst case instance? But I look at some kind of average case on instances generated with a certain random network model, let's say. And then I compare the outcome of this expected running time for various models with each other. and I choose the models in such a way that they are very similar, except they differ in a certain property. And with this, I can basically have a certain property that I can change, and I can observe what is the difference in running time when I only change this property. So I have a very controlled environment where I have these prototypical instances, the generated instances, and I hopefully don't have any other biases. So to do that now, we have to choose some models, and depending on what properties you're interested in, you should probably choose different models. The properties I'm interested in mostly are locality and heterogeneity. And for the rest of the talk, I first want to explain to you what I mean when I say locality and heterogeneity. Afterwards, I give you an example of this method, namely for the bidirectional search I already mentioned earlier. After that, I hopefully motivated you that these random network models I'm looking at are interesting, and then I will give you an introduction. This is then the more tutorial-like part of the talk, where I give you an introduction of how these models work and why they are interesting to look at, and why I specifically chose these models. Okay, so let's look at locality and heterogeneity. So what do I mean when I say locality? I don't want to give you a precise definition of anything, because I don't want to draw this strict line between hard and easy instances, because I said this is pretty hard to do. But instead, I want to give you an impression of what it means that a network is local or has a high level of locality. So I have here two graphs that have the same size. They have the same number of vertices, same number of edges. And one of them I was able to draw nicely. The other one I wasn't able to draw nicely. And this basically means that this has high level of locality and this doesn't have a high level of locality. Or put in different words, what are the characteristics of a high level of locality? Well, I have rather short edges. What do I mean by short edges? Short edges means that if I look at a pair of vertices that is connected by an edge, then these two vertices are already pretty close in the rest of the network. So if I look in this picture up here and I say pick this vertex and this vertex, let's say this edge here, then this edge is contained in a triangle. So even if I delete this edge, you know that these two vertices are somehow close in the network. They have distance only 2. So this additional edge doesn't give you too much information. You already knew that these two vertices were close in the network, and now you give the additional edge, but this edge connects two vertices that are close anyways. In this bottom picture, I don't have this property. There, the edges connect vertices that are far away from each other in the rest of the network. Another way to view this, which is a bit more strict, let's say, is that I have many triangles. So oftentimes I have not only short edges in that sense I mentioned before, but you have a lot of triangles, and you also have a lot of triangles in this specific graphs. There are alternative names you could coin for the same type of concept, and maybe you've heard some of them. So there's homophily. There is clustering, so there's the clustering coefficient to measure something like this. There is the concept of modularity or redundancy. I mentioned earlier that an edge doesn't have a lot of information in this kind of network, because you already knew that the two vertices were close due to the rest of the network. Sometimes you also associate this locality with an underlying geometry, so you are able to place it in a low-dimensional space and have the network structure represented nicely in this geometry. And if you talk to physicists, then they would say this is the low temperature regime and this is the high temperature regime. Okay, so this is what I mean when I say locality. What do I mean when I say heterogeneity? Heterogeneity here refers to the degree distribution of my graph. So what I see here in these plots is on the x-axis I have the degree of a vertex, and on the y-axis I have the number of vertices with this degree. So for this graph, all vertices have roughly the same degree. You have a bit of variation, but you get this kind of bell curve shaped thing where most vertices have roughly the degree of the mean. Over here, you have a bunch of, or let's say most vertices close to the periphery have very small degrees. So this is this very high bar here in the beginning. But then the number of vertices with degree drops quickly for higher degrees, but you still have some vertices with very high degrees. So here in the center of this picture, you have some vertices that have a very, very high degree. So think of heterogeneity as you have a high variance in the degree distribution, or you have a high maximum degree versus many vertices with low degree. And in the homogeneous network, you have a low variance in the degree distribution or a low maximum degree. In both cases, I assume in the following that we have a low average degree. So I'm only talking about sparse graphs. Okay, so given these two properties, I can now look at the space of all the instances, which is spanned by the two properties. So I have in the bottom left corner, I have the instances that are local and homogeneous. Here I have non-local and homogeneous. Here I have the local and homogeneous instances. Here the local heterogeneous, and here I have the heterogeneous non-local instances. Now, I said earlier that I want to analyze algorithms with respect to these properties, and I want to use random network models for that. So the question is, how do we formalize these properties using random network models? And the good news is there are a bunch of random network models out there, so we can basically choose our favorite that falls in one of the four corners. And I want to quickly just mention the different network models for the different corners. I will later on introduce them in a bit more detailed manner. So in the bottom left corner are the classical random graphs, also called Heterogeneity and Gilbert random graphs. They produce homogeneous networks that have a low level of locality or no locality at all, basically. If I want to have heterogeneous networks, there's the so-called Chung-Lu model and the soft configuration model. If I want to have a high level of locality, then one way to achieve that is to look at geometric random graphs. And if I want to have a high level of locality and heterogeneity, then there are, for example, hyperbolic random graphs or geometric inhomogeneous random graphs. So if you don't know any of these, that's fine. I will introduce them later. For now, the important message is for each corner of this space of instances, there is a network model that generates instances that have these properties that are local or heterogeneous. These three networks shown here are, by the way, this is an heterogeneity graph, this is geometric random graph, and this is a hyperbolic random graph. So these are prototypical instances for their respective corner, basically. Now, given these models, we can start analyzing algorithms on these models. So let's get back to the bidirectional search. And for the bidirectional search, Borassi and Natal analyzed the bidirectional search on heterogeneity random graphs and Chung-Lu random graphs with the power law degree distribution. So what this basically means is that they look at Chung-Lu graphs that are actually heterogeneous. And what they prove is that the running time is not linear, but much better, namely square root n for heterogeneity random graphs and somewhere between square root n and linear for Chung-Lu graphs. So if I now have a graph that is that has no locality, I shouldn't be surprised if the bidirectional search is much faster than the unidirectional search. We were able to complete this picture with respect to the locality by seeing that geometric instances, so geometric random graphs, actually don't give you a good running time. There you get a running time that's linear in the size of the graph. But for hyperbolic random graphs, meaning for heterogeneous and local instances, you get a running time that's again between square root n and n. So you again get a better asymptotic running time than for the unidirectional search. Mm-hmm. So with this refined prediction, let's say, let's say what is the refined prediction now? Earlier, the prediction was the running time of the bidirectional search is linear. Now the prediction is the running time of the bidirectional search is linear if you have a high level of locality and have a homogeneous network. So if you are in the top left corner of this space. Otherwise, your running time of the bidirectional search should be much better than linear. This is the new prediction I get from this. So constant speedup if homogeneous and local, asymptotic speedup otherwise. Now, this is for these prototypical instances, right? My real world instances are not randomly generated. They are real world instances. So the question is, how does this generalize to real world instances? And I would say it generalizes quite well. And for that, I have a plot for you that hopefully convinces you that it generalizes quite nicely. So what you have here is on the x-axis, you have the heterogeneity, some measure for heterogeneity. On the y-axis, you have some measure for the locality. So you have the same picture as before. The top left corner is again the top left corner. And now on the left, you have randomly generated instances. So this is the prototypical instances. And here on the right, you have about 1,000 real-world networks. And I looked at basically what is the running time of the bidirectional search on these networks. And the color indicates the exponent of the running time. So if you see a 1 here, which is the red color, you have a running time that's n, so linear running time. If you have something greenish, then you have a running time of n to the 0.5, so square root of n. So now what was the prediction? The prediction was that in the top left corner I should have somehow red color, and in the rest of the space I should have somehow green color, and I think this matches quite nicely in this picture. So I'm not surprised after this prediction, basically, I'm not surprised that most networks in the top left corner have a linear running time, and most networks everywhere else have a much better running time than linear. There are, of course, instances where it doesn't match, right? I mean, this is what I mentioned earlier. This is not a perfect prediction or a strong guarantee. Just because my network lives somewhere here, I'm not guaranteed that this network that the bidirectional search is fast on this network. But I think I would say that I'm at least not surprised that the running time is good if I live somewhere here or somewhere here. This, by the way, also explains how I chose the instances in the beginning, where I said I kind of cherry-picked the instances. The instances where I only have a constant speedup, I picked from somewhere up here, and the instances where I have an asymptotic speedup, I picked from somewhere over here. Okay, so let me make an intermediate conclusion. Let's say, what have we seen so far? I've proposed the following fix for the discrepancy between theory and practice in the algorithm analysis, namely to do an average case analysis on random networks and there look at the difference that we get from changing how much locality and how much heterogeneity we have. And what I've shown you today is some results on the bidirectional search, but there are more results of this type, for example, for vertex cover or satisfiability. I already mentioned earlier that this approach has some pros and some cons, but I think it's worth to mention them again. So what are the disadvantages of this approach? Well, first of all, I have to make some assumptions on the input, and then I have to choose a specific model for my input. And there are a bunch of random graph models I could choose from, and all probably claim to be very realistic, but none really are, at least for a large set of instances. I think you can maybe achieve a very realistic model for certain domains of instances, but they are then very specific to these instances. And if you want to have the really general picture, I think you can't really get to a model, or you have a hard time finding a model that's actually actually realistic on a lot of instances. And moreover, I don't get guarantees for individual instances. I just get that on these prototypical instances, I know how it behaves depending on some property, and then I have to hope that it generalizes to other instances. The main advantage of this approach is that you have an easy way to formalize the properties you want to look at. You don't have to draw the specific line between hard instances and easy instances. You can say, I wish for this property, and then you look at a random network model that has this property, and then you can analyze it. The core question of whether this is a good approach or not is, I think, whether the results generalize well to non-prototypical instances, whether they generalize well to real-world instances or not. And I hope I convinced you, at least for the bidirectional search, this works quite well. So the prediction versus observation part works out nicely for this type of analysis, at least for the bidirectional search. Now, what's next in this direction? Well, first of all, I think it's important to study more algorithms. We don't have that many studied yet, so to really draw conclusions whether this is a good approach or not. And I also think that maybe locality. I believe that locality and heterogeneity are very important, but I would also believe that there are algorithms where other properties are also important. Or other properties are more important, and I think it's interesting to figure out what are these properties and how do the algorithms behave with respect to these properties. Okay, so this concludes the first part of the talk, where I asked the questions: why is theoretical analysis useful? Does it always work? And when it doesn't work, how can we fix it? In the second part, I want to go over the network models I mentioned earlier, namely all these that are mentioned here. And I want to quickly introduce to you what are these models, how do they work? And afterwards, I want to quickly discuss why I think these are good models to study in this context I presented earlier. But maybe before I start with this is a good point in time to ask for intermediate questions. So are there any questions so far that are very pressing? Yeah, that's a good question. The question is, how do I determine the exponent in the running time if I have just one real-world network? So what I basically do is I ignore constants and I ask the question, okay, if the running time is m to the x, then what is the x? So I don't look at, okay, maybe I should backtrack a bit. So I don't look actually at the running time, but I look at the search space. So I look at how many edges do I look at during the execution of the algorithm. And then I assume that this number of edges I looked at during the execution of the algorithm is m to the x, and then I solve this for x. This, of course, ignores constants, but it works quite well in this setting because the constants, I mean, I have to take the logarithm while solving this equation, and the constants in this logarithm, they give you a plus log of something. So if your network is not super small, then this shouldn't change the outcome significantly. Does this answer the question?
I guess.
Okay.
So I also had a question. So
Yeah.
just about the locality thing, I can get the feeling of the definition, but could you like say it again? Like for example, this thing about short edges. So for example, if I take a clique, like a complete graph, you would qualify this as local or non-local?
Yeah, I mean, the clique is a bit of a special case because it's a dense graph, and
yeah,
I'm mainly talking about sparse graphs.
Okay, yes, yeah. Okay.
A clique would be local in some sense, but maybe not in another. But yeah. maybe let me give you an example. So one way to measure the locality would be the clustering coefficient, and the clustering coefficient is the local clustering coefficient is something you can compute for every vertex, and for every vertex you look at how many edges are there in my neighborhood? So you look at the set of neighbors and ask how many edges are there and how many could there be. So if I have 3 neighbors and then there could be 3 choose too many edges, and I count how many are there, how many could there be, and then I get a coefficient of how local I am based on this. So this is a measure for locality. But sometimes this is not really helpful because if you have, for example, a bipartite graph, then you don't have any triangles, but you can still have something rather local in a bipartite graph. And then you can, for example, argue about distances in the graph if you remove the edge or something like that. So there are different ways to measure this. But yeah.
Okay. Thank you.
Question was whether I can give a citation for the measure of locality. I mean, I don't have a citation for that, but if you Google for local clustering coefficient, then you will find it. Okay, any more questions so far? Okay, then let me start with the network models, and I basically try to go from easy to more complicated. So I start in the bottom left corner, go over here, and then go to the top row. So what are Heterogeneity random graphs and Gilbert random graphs? So these are what you often also just call random graphs. And there are two variants of it, namely the GNM and the GNP. So the GNM has two parameters. You have the number of vertices n, you have the number of edges m. And what you do is you take your n vertices and you put all possible edges into a bag, and then you reach into this bag and grab m edges and draw them out. So you draw m edges uniformly with no replacement, and this is then your graph. This gives you every graph with m edges and vertices equally with equal probability. So it's in that sense maximally random with the restriction that you want to have n vertices and m edges. The GNP is very similar, but instead of an exact number of edges, you get a probability for each edge to exist. So what you do is you look at every potential edge, you look at every pair of vertices, and you flip a coin. And if the coin comes up heads, then you create this edge. If the coin comes up tails, then you don't create the edge. And you choose a coin that comes up heads with probability P. So here in this case, I have these three edges. So the coins for these three edges came up heads, so I created these three edges, and the coins for all the other edges came up tails, so I don't create these edges. This type of, this network model is also maximally random in some sense. Namely, if I want to have a network model that where I only put in that I want to have n vertices and that I want the expected number of edges to be p times n choose 2, then this is the model that gives me the most entropy. So in this sense, this is maximally random with the restriction that the expected number of edges should be p times n choose 2. Now, so it's maximally unbiased, and this is something that is a useful property. So you want to know what you put into your model, and everything else you want to choose unbiased in an unbiased fashion, and that is what happens here. You choose how many vertices you want to have, you choose how many edges you want to have in expectation, and then this is the model you should look at. What is the difference between the models? Well, you can certainly choose P so that in expectation you get the desired number of edges in your graph, but this then only holds in expectation. So here you have a hard constraint on the number of edges. Here you have a soft constraint on the number of edges. But apart from that, the models behave very similar. So which one should you choose? Well, choose whatever you like, I think. But maybe as a suggestion, I would say that the GNP is often easier to work with because you have independence between edges. If you already know up here that you drew a bunch of edges, then there are less edges to draw, so every remaining edge is less likely to appear. And here these are independent coin flips, so it's sometimes easier to work with these independent coin flips than with these dependencies you get in the GNM. Okay, so this covers the bottom left corner. These graphs don't have any locality. Everything is chosen independently, so you don't get locality. And you have homogeneous networks, so every vertex has roughly the same degree. If you go in the right corner here, there are again different models to choose from. There is the so-called configuration model, where you can wish for an arbitrary degree sequence, or you should wish for a degree sequence where there is a graph that has this degree sequence. But what you start with is with some degree sequence. So for example, you say vertex 1 should have 3 edges, vertex 2 should have 1, vertex 3 should have 2, and so on. And then from all graphs satisfying this property, you draw one uniformly at random. For example, this one here. This again is the graph, basically it's maximally random with respect to the restriction that you have this degree distribution. Again, this is a very hard constraint. You enforce the degree of vertex 1 to be D1, you enforce the degree of vertex 2 to be D2, and so on. And you can, as for the other GNM and GNP, you can soften this constraint and look at the so-called soft configuration model. And the soft configuration model is somewhat indirectly defined as follows. So for every edge, you define a probability. So for every vertex pair U and V, you define a probability PUV. And then you flip again a coin for this vertex pair that comes up heads with probability PUV. And if it comes up heads, you connect the two vertices. What is the difference between to the GNP model? Well, the difference is that you have different coins for different vertex pairs. And how do you choose the probabilities for the coins? You choose the probabilities for the coins in such a way that you maximize the entropy, so you're maximally random, with respect to the restriction that the expected degree of the vertex D should be dV. So you again want vertex 1 to have degree D1, but now you don't say I want to have it exactly degree D1, but I want to have that the expected, I don't want exactly degree D1, but I want expected degree D1. And when you require that, that completely defines, uniquely defines the values you have to choose for PUV for every pair of vertices. So this is a well-defined model, but it's sometimes a bit hard to work with because the PUVs are somewhat indirectly defined in this way. So if you want to have something that's a bit easier to work with and hopefully not much worse, you can have a look at the Chung-Lu model. There you again choose connection probability for every vertex pair, and you choose the connection probability proportional to the product of du and dv. So you have basically the probability is the desired degree of the vertex u, the desired degree of the vertex d, times the desired degree of the vertex t, and then you normalize it so that you get that all your probabilities give you the degrees you want to have. And if you do that, you actually get that the expected degree of vertex v is dv. And because it's not the same as the soft configuration model, this model is not maximally random, so you have some bias in some direction, but you are kind of close to the maximum entropy model. So this is I think a good model to choose if you want to do some kind of analysis and you want to work with it, but still want to be rather unbiased. And if you want to read more about the differences between configuration, soft configuration, and there's also something like a hypersoft configuration model, then maybe this is the right paper to start with, and there are a bunch of pointers you can follow. Now, I didn't tell you so far what degree distribution you should use, right? I mean, if you now choose that every vertex should have the same degree, then you of course don't get a heterogeneous network. So the question is, what degree distribution should I use? And one that's very commonly used is the power law degree distribution. It's so common that if you say Chung-Lu model, you implicitly assume that you look at the Chung-Lu model with power law degree distribution. What does this mean? Well, it means that if you look at the fraction of vertices of a certain degree d, then this fraction should behave roughly like a constant times d to the minus beta, and beta is again a constant, and it's called the power law exponent. I show you some plots because I think it's much easier to understand with what's going on with plots. So this is some social network, and on the x-axis I have the degree, and on the y-axis I have the fraction of vertices with this degree. So this point up here tells me basically that there is that 25% of the network have degree 1. This point tells me roughly 15% have degree 2, roughly 10% have degree 3, and so on. So the fraction drops quickly, but then you have this kind of this heavy tail where you still have some vertices with degree almost 15k. So this, every time you see something like this, then you should assume it's some kind of heterogeneous degree distribution. Now we don't see a lot in this plot, so let me maybe show you a log-log plot. So it's the same except same plot, except that the x-axis is logarithmic and the y-axis is logarithmic. And what you now see is that if you ignore the initial part here, then you get something that behaves maybe roughly like a straight line. And this is no coincidence, because if you look at the definition of the power law and you take the logarithm of both sides, then you get this equation where you have the logarithm of the frequency, which is what you see on the y-axis. And here you have the logarithm of the degree, which is what you see on the x-axis. And you clearly see that this is an equation for a straight line. With a slope of minus beta, so the power law exponent basically gives you the slope of the straight line. Now, down here you get a lot of noise, and this noise comes from the fact that there are only few vertices with this high degree, and whenever you have only few vertices, you have few samples, and you have a high variance there, so you get this kind of noisy behavior. If you want to get rid of this, one nice way to plot these kind of degree distributions is to do a cumulative plot. So instead of plotting what for every degree, what is the number or the fraction of vertices with this exact degree, you ask what is the fraction of vertices with a degree at least d, and then you get something that in the initial part you often have this somehow curvy shape, but at least for the heavy tail where which describes how the high degree vertices basically are distributed, then there you get a rather straight line here. Now, why do we look at power law degree distributions? Well, if you look into network science, then I think many people say that many networks have a power law degree distribution, but there also seems to be some kind of debate whether it's a power law distribution or not. So if you want to read up on that, there are these two papers, scale-free networks are rare and scale-free networks well done. So if you want to see two different views on this question, then this is where you could look. For our purpose of analyzing algorithms, I would actually say that this question is, I mean, it's interesting and it's certainly worth having a look at, but it's not the crucial factor. I think the crucial factor for us is what properties does this power law have, and is it useful for modeling heterogeneity? And there I would say clearly yes, because if you choose the power law exponent between 2 and 3, then you get an unbounded variance in your degree distribution, meaning you have a high variance in the degree distribution, meaning you have a heterogeneous network. So you can find a regime for this beta where you can somewhat clearly say, well, if I'm in this regime, then I have a very heterogeneous degree distribution. Moreover, you can kind of scale the amount of heterogeneity you have. So if you increase the beta above 3, then you get a bounded variance. So you're less heterogeneous, but you still are not super homogeneous. But if you let beta converge to infinity, then you get a uniform distribution, and you can get actually a homogeneous network. And this is useful if you want to actually generate networks and look at how they behave. You can just scale the beta and get an interpolation between heterogeneous and homogeneous networks. Now, one part I left out, and this is the regime of beta below 2, or beta less or equal than 2. This is basically the dark place, and you shouldn't go there. There you have an unbounded mean, and you will actually have a hard time finding networks because the high degree vertices would need to have a degree that the low vertices cannot provide for the high degree vertices. So for graphs, the regime beta less or equal than 2 is actually not useful to look at. This is why we usually look at only larger than 2. Okay, so now I discussed basically these models down here. So we are done with no locality. Why do we get no locality over here? Well, everything is still drawn independently, right? I still make all the edge choices independently. So where should the redundancy come from? And this is the reason why we are still in the no locality regime, but we have covered the bottom part quite nicely, I would say. Now, how do we get locality? So for locality, you could look at random geometric graphs. And the way you generate these random geometric graphs is by taking some kind of ground space, let's say this unit square, and then you place vertices randomly in this space. So you select random positions for the vertices. And once you have these random positions, the graph is determined by connecting vertices that are close to each other. So for this vertex, I draw a disk of a certain radius, the threshold radius, and every vertex that's inside the threshold radius will be connected to this vertex. And I do the same for every vertex. So this vertex will be connected to these three. This vertex will be connected to these vertices, but not to this because it's slightly too far away, and so on. And if I do that, I get this kind of graph. And I think you can already see that where the locality comes from, right? I mean, the vertex positions are chosen independently at random. Each vertex gets a position independently from all other vertices. But once you know that this vertex is connected to these two vertices, you already know that these two vertices are probably also kind of close and thereby more likely to be also connected. So this gives you triangles and something like short edges and things like that. Now you could look at different variations of these geometric graph models. You could, for example, look at different ground spaces. So if we don't want to have the square because you want to have something more symmetric, the square is rather symmetric, but you get this boundary case here, right? Vertices close to the boundary have probably a little bit lower degree, not by much, but a little bit lower. So you get these edge cases close to the boundary. If you want to get rid of this, you could, for example, look at the torus. So you could wrap around. So basically, if you go up here, you come back from the bottom. And if you go out to the left, you come back from the right. And if you do that, you get, for example, this connection here, which goes out here and comes back in here, or this connection, which goes down here and comes back in here. But so this could be a trick you could use if you don't want to deal with the edge cases around the boundary, but you still have a network model that's rather close to the normal geometric random graphs, I would say. Or instead of the square, you could use a circle. So I think the most common studied random geometric graphs are those in a circle or those in a square. Or you could use different dimensions. So let's say, I mean, this is two-dimensional. Let's say we have just one-dimensional graphs. You place all the vertices on a circle and you connect them if their angular distance is sufficiently low, and so on. Now, this gives you very, very local structures, so networks with a high level of locality. You can actually also scale the amount of locality by adding noise to the generation. So there are different ways you can add noise. For example, you can do random edge swaps. So say you generate your graph and afterwards you pick some edges, let's say this one, and you delete these edges and insert some random edges in place of them. So then you reduce the amount of locality you have, and you basically get a mix between a heterogeneity random graph and a geometric random graph. So you can scale the amount of locality you have if you want to do that. Another way that is not so common in these random geometric graphs, but more common in the heterogeneous random geometric random graphs I want to show in a moment, but I want to address this here because I'm right now talking about noise, is the concept of temperature. So in the normal geometric case, you have this threshold distance, and if you're below this threshold distance, you have a connection. If you're above the threshold distance, you don't have a connection. So you basically have some kind of step function for the probability to have an edge depending on the distance. So for distance in this area, you have an edge. For distances in this area, you don't have an edge. And this is typically associated with a temperature of 0. And now you can soften this by looking at some kind of sigmoid function. And the higher the temperature, the less steep this sigmoid function is. So you don't have this sharp threshold, but instead say, okay, I have a probability for having an edge depending on the distance, and the larger the distance, the lower the probability, the smaller the distance, the higher the probability. And with this, you can also scale basically the amount of locality you have. Okay, so this gives us the geometric networks, and you are able to scale towards the uniform, towards the non-local networks. Now what remains is the top right corner. And there I want to start with the so-called geometric inhomogeneous random graphs. They are abbreviated usually with GERG, and they are basically a mix of the geometric random graphs I just showed and the Chung-Lu random graphs I showed earlier for getting heterogeneity. And you then get basically the best of both worlds and have heterogeneity and locality. So how do you do it? You have two things. First of all, you have a degree distribution, or you have degrees you want to have for your vertices. And in addition to that, you draw random positions for the vertices in some d-dimensional ground space. For example, a unit square or whatever. And then for every edge, you look at the distance between the two vertices and you look at the product of their desired degrees. And if you ignore what's on the right-hand side and only look at the left-hand side of this inequality, then what this basically tells you, and I have some kind of normalization with respect to the dimension, but I think it's okay to ignore that for now. So if you just look at the left-hand side, then you have the distance between the two vertices, and this basically says, okay, if the distance between the vertices is sufficiently small, then I connect them. So you get the locality from that, because this is basically just saying I have a geometric model. If you look on the other side, then you basically say, okay, what I have on the left side, this is a random variable. So there, the distance between two vertices is something that's determined by their random positions. So this is a random variable. And the normalization makes it so that behaves kind of linearly, this random variable. And now I create an edge if the product of the desired degrees is higher than this random variable, which basically means I create a connection with probability proportional to the product of the degrees, which is exactly what we did for the Chung-Lu model. So basically looking at this side, you get the locality from the geometric model. Looking at this side, you get the heterogeneity from the Chung-Lu model. And this is basically just the combination of the two and nothing more. There are different models that are very, very similar, but come with different names and slightly different interpretations. And I want to mention two of them, namely the popularity-similarity model, where you basically say, okay, I have exactly these two things. I have a similarity between pairs of vertices, and I have a popularity for every vertex. And the similarity is, and I interpret these two things not as the similarity is the geometry and the popularity is some kind of degree I wish for, but I interpret it as these are two dimensions of a geometric space. So I also interpret the popularity of a vertex geometrically. So if I have these two vertices here, so I basically have positions in the circle for every vertex, and I have these two vertices here. They have a certain angle, and the angle gives me the similarity. The smaller the angle, the more similar they are. And the distance from the boundary gives me the popularity. And the further in the center they are, the more popular these vertices are. And now I do basically more or less what's written up here. If the similarity is sufficiently high, meaning the angular distance is sufficiently low compared to the popularity of these two, then I make a connection. Otherwise, I don't. So in this case, if you can generate a graph using this, and in this case, these two are sufficiently popular. I mean, they are not super close, but also not super far away with respect to similarity. And they are both rather popular. So I create an edge between them. And this gives you this kind of graph. Now, what you can now do is you can define some kind of metric on these points that basically represents this decision of creating an edge. Taking into account similarity and popularity at the same time. And if you do that, you will find out that what you're actually working with is hyperbolic geometry. So if you don't know hyperbolic geometry, that's okay. But what you basically could do instead of thinking about popularity and similarity is you could choose a disk in the hyperbolic plane. And in this disk, you sample vertices uniformly at random at positions drawn uniformly at random. And then you connect two vertices if their hyperbolic distance is sufficiently small. And this does basically the same as what I mentioned up here. And it basically does the same as what the popularity similarity model does. But it gives you this nice, purely geometric interpretation of what is going on instead of having these two different concepts of similarity and popularity. Okay, so this covers the top right corner. Now, quickly, why these models and why not different models? I mean, there are a bunch of different models out there, and maybe you already have your favorite models and they didn't show up here. And maybe I can, maybe this slide explains why I chose these specific models. So I think you can have different, I think that the type of model you should choose depends on the question you want to ask. And I think there are at least two questions you could ask. One question is, if I look at a bunch of networks and I see they have a certain property, I could wonder why they have this property. So let's say I look at a bunch of real-world networks and I see they have a high level of locality, then I can ask the question, why do they all have this high level of locality? And another question you could ask is, assuming I observe that networks have locality, and now I assume that a network has locality, what can I deduce from this assumption? And I think these are very different questions, and I think you should probably use different network models depending on which question you want to answer. So if you want to explain where a property X comes from, then you probably want to assume some simple mechanism that is based in the real world, like, for example, preferential attachment. You always, new arriving vertices connect to vertices that are already popular in the network. This is preferential attachment. And from this assumption, you can deduce that the graph has a power law degree distribution. So you make a simple assumption on some mechanism, and from this assumption, you derive that the networks have a certain property. So I think this is what you should probably do if you want to answer the first question. If you want to answer the second question, then I think you should do something different. You should instead explicitly enforce the property you are interested in the network, and otherwise try to keep the model as unbiased as possible. So try to find a maximally random network model that has the property and then study how it behaves because of this property. If you instead use something like preferential attachment, then you're not as sure as whether the thing you show comes from the property of having the power law degree distribution or some other property that comes from the preferential attachment process. And the network models I showed you, the network models I showed you earlier fit very well in this category. You have the properties you specify the properties you want to have, namely heterogeneity and or locality, and then you generate networks that are as random as possible given these properties. Okay, so let me conclude. I had basically two parts today in this talk. The first part was about theoretical algorithm analysis, and there I showed you that the analysis or the predictions you get from theoretical analysis sometimes fails, and that you might be able to fix this by making a more realistic algorithm analysis by doing it on random network models with varying properties. And these random network models then provide you with an idealized setting where you can study the behavior of algorithms depending on certain properties. And in particular, I showed you this for the example of the bidirectional search with respect to locality and heterogeneity. And the second part, maybe one thing I want to stress here is that this approach has advantages and disadvantages. The disadvantage is that you cannot guarantee that you don't get performance guarantees for specific networks, but it seems to, at least for the bidirectional search, work quite well because the results you prove on this idealized setting seem to translate to real-world networks over here. And in the second part, I try to give you a very brief introduction into the network models I used for this, or that are useful for this kind of analysis, which were the Heterogeneity and Gilbert graphs in the bottom left corner, the soft configuration model and Chong-Lu graphs in the bottom right corner, geometric graphs in the top left corner, and geometric inhomogeneous random graphs, hyperbolic random graphs, and the popularity similarity model in the top right corner. And this picture, by the way, this is here, you see only GERCs. These are the geometric inhomogeneous random graphs. I mentioned earlier you have this concept of temperature, which lets you scale the amount of locality, and you can scale the amount of heterogeneity by changing the power law exponent. So you can just use the geometric inhomogeneous random graph model to generate all these networks in this picture and get somehow an overview of what changes depending on heterogeneity and locality. Yeah, that's all I have, and I'm open for questions.
Thank you very much. That was a great talk. I think I understood a lot more about the network models. Yes, simply great. Are there any questions?
I have a question, but maybe someone in the audience wants to ask a question. Someone else. Okay, so people are shy. Yeah, I was wondering. So here it seems. I mean, when looking at these pictures, it looks almost magical. Like it's really like it captures what you want to capture. So, is there some intuition about why here it's so good? Like basically, you have like here 3 elements. You have the problem you study, which is this bidirectional search. You have these 2 parameters like locality and heterogeneity, and well, it looks like these 3 things go well together. So I don't know. Could you give some intuition about like could it work just as well for another problem? Like are these 2 parameters or these 2 properties say really somehow fundamental for networks, or is it something of this problem or something like this?
Yeah, so I think, I mean, if you look in the details of the proof, you can kind of figure out why it works in this setting. And the reason for why it works for the bidirectional search is how search spaces expand. So if you look at how does what is the number of vertices that have distance at most d from my source vertex, and you look at how this expands, this behaves very similar if you have no locality or if you have a high level of heterogeneity, and it behaves very differently if you have locality and homogeneity. So this is the underlying reason why it works well here. But you also have other problems. I mean, as I said earlier, we still need to study more problems to figure out whether this is just accidental in some cases or whether these properties are actually useful. But at least for the vertex cover problem, there are, I mean, it's an NP-hard problem, but there are some kind of reduction rules with which you can try to reduce the size of the instance. And for this, I can say a similar, you get a completely different picture. There are different places where it's red and different places where it's green, but it works similarly well. And also for SAT solving, there the picture is not as clear. But again, you have this thing that theory on these models tells you that if you have locality, then it should work well. And in practice, you observe that you can solve these instances that have a high level of locality work well. And also, I think if you want to enumerate cliques or things like that. So there are other examples where it works similarly well. I don't have a conclusive answer to this question, because I think we need to study more algorithms and see whether we need other properties. But my impression is that these 2 properties are already pretty powerful.
Okay, thank you very much.
maybe directly related. So in parameterized complexity, for example, tree width is one of the most studied parameters. And especially for the NP complete problems, they can be solved faster than in general if the tree width is bounded. Does this appear somewhere in your studies?
Yes. So if you look at these random networks, then in the basically, if you have locality, then you have a lower tree width, and if you don't have locality, you have a high tree width. But I think this is not. I mean, the degree width is not. I mean, this suggests that high level of locality makes it easier for many problems, and I would agree that this is the case for many problems, for many hard problems. But the tree width you get is not as small, not small enough so that it can really explain why things work, I would say. So for geometric random graphs and also hyperbolic random graphs, you get tree widths that are somewhat like square root n or something like that. This is good, right? You can do things with that and you can use this algorithmically, but it's not so good that you can say I can now solve vertex cover.
Okay, and there is a question in the chat.
Yes.
Are you aware of any works that study the same questions as you in different models of computing, for example, streaming or distributed computing?
No, I'm not aware of that, but I think it's a very interesting thing, and I would be surprised if having this concept of having some kind of formalization of the concept of locality wouldn't help you to do better distributed algorithms, or to at least analyze them in a better way. Because if you don't have locality, then you have a hard time clustering your instance basically and solving maybe sub-instances in a distributed fashion. And if you have a high level of locality, it should be easier to solve your instance in a distributed way. But I'm not aware of results in this direction specifically, but if someone else has results in this specific direction, I would be highly interested in that.
Are there further questions?
I mean, maybe to add to that, I mean, there are, there are works that are, let's say, between what I told you today and distributed computation. For example, if you want to generate networks from these models, this is also a problem that's not always trivially to do efficiently. And there are works that try to do this in a communication-free way, distributed way, and highly parallel. So there are works in this direction.
Yes, I think it may be very interesting. Like, it's not a realistic assumption to say your graphs are planar. This is simply too restrictive. Your models seem to fit much better to real practical networks. And this should be very interesting also in the distributed community. Yes. Okay. Are there further questions?
So I guess I had a somewhat vague question. Sorry, you might have said this in the first half. I missed the first half of your talk. It's kind of early in North America, so I came in a bit late. But I really liked this distinction you made at the end between the two types of questions, and we all need different models for those. It seems like in some sense there's a very easy but very unsatisfying answer for the second one, which is maybe what you were getting at, but I wonder if it's usable at all, which is, if I have some parameter and I want to be maximally, or I have some kind of property and I want to be maximally random on the rest, like there's kind of an obvious way of doing that, right? Like say I have the uniform distribution over all graphs that have this property, right? But that seems like impossibly hard to work with and like super difficult. Is that kind of what you're suggesting, that we work with that distribution, or that we kind of find more reasonable distributions to work with?
Yeah, I agree. This is super hard to work with. And for example, for this Chunglu graphs here, so if you don't have locality, you can still do that and work with the maximally random distribution. So this works. For example, the soft configuration model is maximally random, and there are works on that. But I think if you want to analyze an algorithm on that, you probably have a hard time, and it's much easier to work with the Chunglu model, which is way easier to work with, very similar to the soft configuration model, but not quite maximally random. And this is what I say is what I would say is probably the way to go to maybe not enforce maximal randomness, but at least try to achieve that and try to avoid biases. And in the setting where you get to the high locality regime, there it's even harder, because there are so many different ways to define what locality means, and none of them are really satisfying. And it's really tough to come up with something there. So there in particular, even if you fix a definition, it's completely unclear how this probability distribution looks like and how to work with it. So there it's really difficult. And the way out of this problem for locality right now is to say, okay, I model locality by assuming a low-dimensional geometry underlying my data. So this is right now basically what I accept as, well, this is a reasonable assumption, and it's still and with this assumption, I'm maximally unbiased after I make this assumption.
Awesome, thanks.
Great. So thank you again, Thomas.
You're very welcome.
Really a very nice talk and very enlightening. I propose that we have 2 minutes of break simply now before we start with the talk of Michael. Okay, so see you in 2 minutes. Thanks.